Hi, hi everyone. I'm Dr. Chanba Tirupati, Associate Professor, Head of the Department, Head of the Civil Department, Session Institute of Technology. In today's session, we are going to discuss about surface tension. So till now we have discussed a few fluid properties like mass density, specific gravity, specific weight, and specific volume, bulk modulus, and compressibility, and dynamic viscosity and kinematic viscosity. So today we are going to discuss about seventh property, that is called surface tension, right? Yeah. So what is surface tension? So surface tension is a tensile force acting on a fluid for unit surface area. So for example, if you see, it is defined as the tensile force acting on the surface of a liquid when it is contact with a gas or a air, right? And also when the two immiscible liquids in contact. So what is meant by this immiscible liquid? The liquids does not form homogeneous mixture when they are mixed. So means two different molecules. For example, if you take some water and if you pour into the oil, and if you mix oil and water, they are not form single liquid, right? So they are two different molecules. They will not interact with each other. So that kind of liquids, two immiscible liquid. So what is the surface tension? Surface tension is the tensile force acting on a liquid surface when they are in contact with air or a gas or a two immiscible liquid. So normally it is represented as a tensile force for unit length. So the force, tensile force acting for a unit length, and also it is represented with the symbol sigma, right? So what is the tensile force? If it in newtons for unit length. So the units for surface tension is Newton per meter. So how the surface tension will be helpful? I think you may wonder, like if you see insects will walk on the water, and if some needles or blade, if you put into the water, they will float on the water, right? How it's happening? It is because of the surface tension. And also in toothpaste we will use the soap. So what it will do is it will reduce the surface tension, so it will allow the toothpaste to flow in our mouth. So that is one of the important applications surface tension we use in our daily lives. So now we will discuss in detail about the surface tension. So simply the surface tension is the tensile force acting for unit length of the surface of the liquid. Okay. Yeah. So how this surface tension phenomena will occur? For example, if you take one container, I have taken one container and we have a liquid up to here. So this is the liquid in the container. So I have taken one container which is having a liquid. For example, if I consider one liquid molecule here, so one liquid molecule here, what will happen? If I consider one liquid molecule, so whatever the liquid molecule here, so we'll try to pull that liquid downwards because of the molecular attraction between the liquids. So what you can call as a molecular attraction between the same molecules, that is cohesive force. That is called cohesive force. Because of the cohesive force, see that adjacent liquid will try to pull these liquid molecules downward, and also there may be another liquid here, so it will try to drag in this side, and in upward there is a one more molecules, and here one more molecules, here one more molecule. So whatever the molecules nearby or adjacent to these liquid molecules will try to drag this molecule to their directions. So if you see here, these all the liquid molecules adjacent to this liquid molecule will apply equal and opposite forces, right? Equal force, right? So because of this, the liquid molecule here, it will be in a neutral condition, or will be in a equilibrium conditions. So this will happen inside the liquid because one liquid molecule is surrounded by the all other liquid molecules. So what will happen if I consider a liquid molecule here? So I consider one more liquid molecule here. So if you see, the liquid molecule here will try to drag downwards, same here left side, then right side, and here. So but if you see, the upward forces very less, right? So upward forces are very less and downward forces are high. So because of this, the overall net force will be downwards. So the liquid molecules is dragging towards downwards, but here sigma F, some of the forces will be 0. So that's why this fluid molecule will be neutral conditions. So what will happen if I consider the liquid molecule at the surface? So at the surface, see here, the liquid molecule acting downwards, right? Yeah. So at the surface, so what will happen at the surface? So these two adjacent liquid molecules will try to pull towards their side, right? So because of that, the surface here will be like stretched. It will act like a membrane. So that force you can call as a tensile force. So here it will act tensile force. So it will apply some tension, right? So because of this, for example, if there is an insect here, so whatever the weight applied by the insect on this surface, if it is less than this tensile force, so it will float. It will not sink into the water. So that's why if you see needle or a blade, so it will float on the water. So this force you can call it a tensile force acting on the surface of the liquid. So here this is air, right? So when the liquid molecules contact with the air, so this you can call as a surface tension. So what is the surface tension? Surface tension is represented with sigma. It is a tensile force acting for unit length of the liquid. I hope you understand this concept. So the main reason for the surface tension is, see, if you see, because of the cohesive force, the liquid molecules are attracted to each other, right? So what are the liquid molecules adjacent to the other liquid molecule will try to attract towards that. So here at the inside, so it will be neutral condition, right? It will be in neutral condition because all the forces, all the liquid molecules surrounded by this liquid molecule will attract towards their direction. So some of the forces will be 0. Here if you see near the surface, so the downward forces are dominant than the upward forces. That's why the liquid molecule will pull downwards. But at the surface, see, these two are equal and opposite and parallel forces because they will stretch the liquid molecule, so it will act like a membrane. So this is called surface tension. Anyway, we will discuss in clear and we will try to solve some numerical problems too on this concept. Okay. Now we will try to derive the expression for surface tension on a liquid droplet. For example, if you consider, sorry, ఇక్కడ నుంచా మ్యామ్
సైడ్ ఏరో మార్క్ ఉంటుంది సార్, అక్కడ లాస్ట్ లో క్లిక్ చేస్తే పెన్ వస్తుంది
ఇది. ఓకే మ్యామ్, థ్యాంక్ యూ. ప్రతిసారి ఇలానే టైం వేస్ట్ అవుతుంది. ఓకే, ఇది కట్ చేయండి, మళ్ళీ స్టార్ట్ చేస్తా ఇది టాపిక్. ఓకే, now we are going to derive the expression for surface tension on a liquid droplet. Okay, now I have considered a liquid droplet, a spherical liquid droplet, right? So this is the droplet I have considered. Now I have cut the droplet into two halves, right? I have cut the droplet into two halves. See, the radius of this droplet, so what you can say, the radius of this droplet is, for example, the radius of this droplet is r. The surface tension acting on the droplet is sigma. I have considered the surface tension acting on the droplet is sigma. Now if I cut this droplet into two halves, so what are the forces will acting on the droplet? So inside there will be a pressure, inside there will be a pressure acting on the droplet, and surface tension will act along the circumference of the droplet. The surface tension will act along the circumference of the droplet. For example, this is the droplet, so surface tension will act, right? And so every point, the surface tension will act along the circumference of the droplet. So what is the total surface tension acting on the half of the liquid droplet? So that will be equal to what? Sigma surface tension into circumference, right? Circumference. What is the circumference of the cylinder? sorry, circumference of the sphere, it will be pi d, sigma into pi d, right? Sigma into pi d is the total surface tension acting on the circumference of the droplet. Now, what is the pressure acting inside the droplet? See, this is the pressure acting inside the droplet in excess of outside pressure. That is a very important concept, right? This is the total pressure acting inside the droplet in excess of outside the droplet. If you see the outside the droplet, there will be a air pressure, right? Atmospheric pressure will acting on the outside the droplet. So what are the pressure here inside? It will be the pressure acting inside the droplet in excess of outside pressure. What is the pressure force? You know what is the pressure? Pressure is equal to force per unit area. So what is the total pressure force? That will be equal to pressure intensity into area of the droplet. So what is the pressure intensity? P, and area of the droplet is pi by 4 d square, right? This is the total pressure force acting inside the droplet in excess of outside pressure. So this is the total surface tension acting along the circumference of the droplet. So when the droplet is in equilibrium condition, so when it is in equilibrium condition, so these two forces will be equal and opposite to each other. So these two forces will be equal and opposite to each other. So that means sigma into pi d will be equal to P into pi by 4 d square, right? So pi will cancel and d, so both are same d, right? So d will cancel. So then what is the required expression? We need to find out the inside pressure. P is equal to 4 sigma by d. P is equal to 4 sigma by d. This is the expression for pressure inside the droplet in excess of outside pressure. This is the very important thing you should remember, right? If you observe this, if the diameter of the droplet increases, pressure will be decreases. If the diameter of the droplet will decrease, then pressure will increase, because these are inversely proportional to, right? So when the size of the droplet is very, very less, so the pressure inside will be very high. So this is the what you need to understand. I hope you understand this concept. Now we will try to solve some numerical problems, and also we will derive the expression for droplet soap bubble, right? Okay. Yeah. Okay. What happened if you take a soap bubble? So soap bubble, if you consider a soap bubble, so what will happen? So inside there is a halo, right? Inside there is a halo. For example, this is the thickness of the soap bubble. Inside also it will be halo, right? So the pressure acting here outside, and also pressure will acting inside, right? So the surface tension will act here outside the droplet and here also, right? Both, two circumferences. What is the total surface tension will act? 2 into pi d, sorry. Sigma is equal to, okay, yeah. So it will be equal to, this is the total surface tension acting on the soap bubble, sigma into 2 pi d. Why 2 pi d? Because two surfaces, right? This is also contact with the atmosphere, and this is also contact with the atmosphere. So the liquid molecules, whatever the contact with the air, will have a surface tension. So 2 times. So this is the total tensile force acting on the soap bubble, right? So next one. So what is the pressure? So pressure is equal to force into area. We already derived. So that is, we required force acting inside the droplet. That will be pressure intensity into area. That will be P into pi by 4 d square, right? So when the liquid droplet is in equilibrium condition, these two are equal and opposite to each other, right? So that means sigma into 2 pi d will be equal to P into pi by 4 d square. So d will cancel, pi will cancel. So P is equal to, P is equal to 8 sigma by d. So this is the expression for pressure inside a soap bubble. Similar relation, if diameter increases, pressure will decreases. If the pressure increases, diameter will decreases. I hope you understand the expression for surface tension for both liquid droplet and a soap bubble. Now we will try to solve numerical problems. Okay. Now, yeah, this is the first problem. What is given? Find the surface tension. So you have to find out, yeah, what you have to find out? You have to find out the surface tension. This is the unknown. So find the surface tension in a soap bubble. So what is given? Soap bubble, right? What is the expression for pressure in a soap bubble? P is equal to 8 sigma by D, right? Of 40 mm diameter. So the diameter of the soap bubble is given. How much? 40 mm. So what is 40 mm? You have to convert into meters. Why we have to convert into meters? Because see, the pressure is given in Newton per meter square, right? So if you convert into meters, it will be 40 into 10 power of minus 3 meters. Next, when the inside pressure is 2.5 Newton per meter square above the atmospheric pressure, that means pressure inside the droplet in excess of outside pressure. That means P is given. P is equal to 2.5 Newton per meter square, right? So this is the formula. So we know sigma we need to find out, P we know, and diameter we know. It's very easy, straightforward, you have to substitute, right? So if you substitute these two values in the equation, it will be 2.5 Newton per meter square will be equal to 8 into sigma by 40 into 10 power of minus 3 meters, right? So then this is 2 times 10 times, right? 5 into 2.5, how much? 10 and 15, oh sorry, 7.5, right? Okay, sorry, 10, no, yeah, 12.5 into 10 to the power of minus 3 Newton per meter. This is the surface tension, right? 12.5 into 10 to the power of minus 3 Newton per meter. This is the surface tension. I hope you understand this problem. Shall we go to next problem then? Yeah. Okay, this is the solution. Now we will try to solve second problem. Okay. Now second problem. So the pressure outside the droplet of water of diameter 0.04 mm is 10.32 Newton per centimeter square. That is atmospheric pressure. See, carefully read the problem. The pressure outside the droplet. So pressure outside the droplet is given, right? So pressure outside the droplet. Pressure outside the droplet is given. How much? 10.32 Newton per centimeter square. So that is in mm, this is in centimeters, and here it is meter. So we have to convert all the variables into single units. So I will try to convert all the units into single variable, single units, that is meters, right? So that means 10 to the power of 32 into 10 to the power of minus 4 Newton per meter square. If I convert into Newton per centimeter square to Newton per meter square, okay. Next, second, the diameter of the droplet is given. So diameter of droplet, that means D is given. How much D? It is 0.04 mm, right? 0.04 mm, that means 0.04 into 10 to the power of minus 3 meters. Clear? So next, you have to calculate the pressure. So what is the unknown? It is pressure, right? So P you need to calculate. Yeah. Within the droplet, if the surface tension is given as, so surface tension is given in the problem. How much it is? 0.0725 Newton per meter. So we no need to convert this surface tension into any units because this is in meters, right? So what is the formula? Here the pressure outside the droplet of water diameter. So he has nowhere mentioned it is the soap bubble, right? So it is a normal liquid droplet. So what is the formula? We know, right? P is equal to 4 sigma by D. What we need to find out? We need to find out P, and we required this we need to find out. Surface tension is given, and diameter is given, so it's very straightforward. We need to substitute here, then we will get the answer, right? Okay, now okay, I will try to solve here only. So P is given, how much P we need to find out, right? Yeah, 4 into surface tension 0. How much? 0.0725 Newton per meter by D. D how much? 0.004 into 10 to the power of minus 3. So if you solve, how much you will get? Will be 0.725 Newton per, sorry, 7250 Newton per meter square. Okay, we will keep, or otherwise we will keep in Newton per centimeter square. 0.725 Newton per centimeter square. So the answer will be 0.0725 Newton per centimeter square, right? Okay, now this is the pressure inside the droplet in excess of outside pressure. What is the outside pressure? Excess outside pressure is given as 10.32 Newton per centimeter square. This is 0.0725 Newton per centimeter square. This is, see, I will tell you. See, this is the soap bubble. So what is the P you consider is the inside the pressure, like what is the pressure inside, and what is the outside pressure? This one, right? 10.32 Newton per centimeter square is outside pressure, and the inside pressure is 0.0725 Newton per centimeter square. What is the total pressure? If you add both, you will get the total pressure acting on the bubble. So if you add these two, it will be 10.32 plus 0.037. So it will be 11 point, oh, it is point, okay, sorry. Yeah. Okay. It is 0.725. 10.32 plus 0.725. So you will get total pressure is 11.25 Newton per centimeter square. So here you need to understand. So what is the P here? It is only the pressure inside the droplet in excess of outside pressure. So he is asking about to calculate the total pressure. Calculate the pressure within the droplet. That means inside pressure plus outside pressure. So then you will get the total pressure. Okay, I hope you understand this problem. Now we will go to next problem. This is the third one. Okay. Now the surface tension of the water in a contact with air at 20 degrees centigrade is 0.0725 Newton per meter. So surface tension is given 0.0725 Newton per meter. The pressure inside the droplet of the water, so P is given 0.02 Newton per centimeter square greater than the outside pressure. So simply the pressure inside the droplet is given. So calculate the diameter of the droplet. So you have to find out the diameter of the droplet. It's very straightforward problem. So we know that it is a normal droplet, right? So P is equal to 4 sigma by D. So we know P and we know sigma, we can calculate the diameter. So what is the P value here? It is 0.02. Oh, it is in centimeter square. You have to convert into meters because this is in meters, right? So it will be 0.02 into 10 to the power of minus 4 Newton per meter square. So into 10 to the power of minus 4 will be equal to 4 sigma. Sorry, sigma we know, right? Sigma is 0.0725 divided by what is the diameter? Diameter we need to find out. So if you solve this problem, so you will get answer around 1.45 mm. So finally you will get the diameter of the droplet is 1.45 mm. This is the diameter of the droplet. Yeah, I hope you understand the concept of surface tension, and we already solved few numerical problems. So this is the very important concept in terms of fluid properties. We will meet you in the next session. Next session we will discuss about capillarity, and also we will try to solve few problems, numerical problems related to capillary action. Thank you for your attention.